Okay, we've got, yeah, I'm recording. We've got this complicated, horrible expression here is the expectation of x to the power 5, where x is a binomial random variable with size capital N and probability p. You see, in all of this, capital N and p are fixed, so we just substitute them in. They don't change. They're not random. All right, what I'm going to do is the expected value of x cubed. Bonk. Don't like that. Oh, it's because it's EXN. Right, which is that stuff there, and maybe I can simplify it as well. Full simplify. Bonk, donk. Brilliant. Now, watch how I do this. I have been fiddling around with it before. So what I'm going to do is describe Sage as a function of n and p, which returns this thing here. I'm not sure if I can cut and paste it actually. Can I cut and paste it? Maybe I can. Maybe if I do that and do it again. Ah, that's nice. Right, so I'll cut that, copy, go back to R, which is here, and paste it. Ha! So now I can verify in R the Sage thing. I think that should work. So let's try it with 10, 0.345. I'm just making some numbers up. And it comes out to be 65. So what I'm saying is that the expectation of binomial random variables, let's try that. Random numbers from the binomial distribution. We'll have 100 of them. Size 10, so we're going to do 10 trials. Probability of success 0.345. There you go. Some are 2, some are, you know, it's random, yeah? So I'm going to work out that cubed, because look here, it's a 3. There you go, it's a 3. So if I go back to R, where is it here? Jonk, blonk, there you go. Look, and it's doing 125, that must have been a 5, cubing 5, that must have been a 7, and so on. So we're going to work out the mean of those guys. And if I do it again and again, you see there's quite a lot of variability because I've got a very small sample size of 100. So I'm going to just have 100 million. No, that's 10 million. There we go. And now, if I do it repeatedly, I've got very small variability. Now what does Sage say? There's my function. All I've done is type in this thing here is this thing here that Sage gave me. So I'm just going to plug the numbers in. Sage of 10, 0. What was it? 345. 345. 65 point, look at that, 65.15, and here it comes up 65.14, and of course these aren't exactly accurate because of the finite sample size, but it's showing us that numerically at least we're getting good verification that the two methods, direct numerical simulation here, is agreeing with this one here, which is that function here, which comes from this function here, which comes from all this stuff with the moment generating function, which is quite nice. It's quite nice. When you see a result, you should always try and verify it numerically, at least I do. It's a lot more convincing, a lot more satisfying, a lot nicer to do that than just to write it down. Just see if it works in practice. Actually, I could do it a lot harder. Well, let's try this one. Let's try this one here. Blonk. Whoa, look at that. Let me try that one. Here we go. So I'll go Sage 5, call it, becomes a function of n, p, parameters of the binomial distribution. Oh no, I didn't like that. Bong, 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 bong. Let's grab, copy. And it might not work because it might not like the new lines. Don't think it like that. Sage 5 of, let's say, 10 again. Oops, 10 and 0.345. Oh, it worked. I'm surprised because I'd have thought that the new lines here would kind of interfere with ours interpreter, but it hasn't. Okay, well, we'll just go through the same process again, but instead of to the power 3, it's going to be to the power 5. Look at that. Isn't that brilliant? Look at that. It just agrees. So let's just summarise the whole thing. The whole thing is this. First of all, we get the moment generating function here, which we got from Wikipedia. We differentiate it. We substitute t equals 0, and that gives us the expectation of the random variable, which in this case is binomial, to the power lowercase n. Lowercase because it's this one here, right? And then what we do? We put 5 in there, so this expression here is the expectation of our random variable to the power 5, because I told it. I could have put any number in there. Try 15. Look at that. What a mess. What a mess. I'm going to typeset that and do it again. Jonk. See, it takes quite a long time. Look at this. What a pig's ear this is. Look at it. I'm not even sure I can scroll to see all of that, but there it is. Right, and then we can verify that in R here. Wonderful. Right, I'll see if I can use Sage to derive the moment generating function, but I'm not sure about that. I'll need to think about that. I'm still recording. How do I stop? Stop.